Good morning. I'm very excited about this panel here because it's a positive one. It's success stories, right? So it's things that have turned out well, and we're here to talk a little bit more about some of maybe the struggles that occurred on the way, but overall, what worked in terms of making team science a reality. So as Dr. Friedman said, I'm Alice Park. I write about health and medicine for Time, and I'd like each of our panelists to just briefly introduce themselves and their affiliation.
Michael Goldblatt. I was with Functional Genetics till the beginning of the month, and happily it's transitioned now to a larger partner organization, so I'm now looking for the next adventure. Prior to that, I am an example of a failed classics major who had to transition after a junior qualifying exam to biochemistry, and then from biochemistry advanced degrees in nutritional biochemistry, law, and ag engineering, and then took a career path to General Foods Corporation, where internally I was involved with the development of or the use of nutrients for pharmaceuticals. Externally, I was involved in creating organizations to work on global technical problems among a common competitive interest, where we brought competitors together to work on global technical problems. And from there to McDonald's Corporation, where I was Chief Technology Officer responsible for nutrition, food safety, corporate venture capital, and strategic design. And then had a congressional appointment to the Department of Defense to create biology as a future historical strength within the Department of Defense in DARPA. And from there to functional genetics, where for the last 10 years we worked on transitioning or changing the paradigm of infectious disease, going beyond killing the pathogen to save the host, to targeting the host to deny the pathogen the ability to create disease.
Well, I wear several hats. Right now I continue to be at the MIT Koch Institute for Integrative Cancer Research. I'm an engineer. I'm at the interface of engineers and biologists. That's largely what sort of brought me to, I guess, the questions of team science. And as a result of some of our work, my work, we've had 2 spin-outs. I lead one of those to get it to the clinic, and so I'm a CEO of a company. Prior to that, I was at Arthur D. Little. Many of you might not have been born back when Arthur D. Little was at its prime, but it was a big consulting firm. I managed the technology business, and decided after a while that I wanted to move out of the hard technology business and get involved in cancer research, and that's what I did in 2003. And brings me to my work at MIT. I wanted to understand how engineers and biologists work together, because that was my role, and I thought I could look back and see how other people were successful. What I found interested me so much that I wrote a book on it, which was just published this month. I see a copy outside, thank you, by the MIT Press. And as I told folks here, that what I found is not just the successes of team science, but I felt more importantly, what happens when you don't have team science? What does it cost in terms of time and elapsed time to getting to the goal? And that's what I hope we get a chance to talk about.
So my name is Michael Nielsen. I'm an independent writer and consultant. My background is as a theoretical physicist. So I worked through the 90s and the 2000s for about 15 years on quantum computing. My connection here today, I guess through all that time, I observed a lot of, I guess, interesting phenomena everybody here is familiar with, things like the Linux operating system or the Wikipedia and things like this. And these are certainly collaborations, but they're very strange from a conventional point of view. They were started in many cases with no funding, no money, no grant agency involved. And they're very unusual in a large number of ways. And I got interested in the application of the same kind of ideas within science, not just theoretical physics, but science and research more broadly. And I spent the last few years working on a book about networked science, which describes some of these ideas and how some of them can be imported into science.
So it's interesting you have a panel that's bracketed by people interested in classics. I was actually a classics major in addition to biology and computation and logic at Stanford. And I am, by career trajectory, I'm on the faculty in genome sciences and medicine at the University of Washington. I'm a fully trained MD and oncologist, but I run a basic science laboratory in the Northwest Epigenome Center and the UW High Throughput Genomics Center. And I have been involved in several team science projects, including the project called the ENCODE project, which is sort of a successor to the Human Genome Project. I try to map all of the functional pieces of the human genome that's been going on now for it's in its third round, really. Started back in 2003, a parallel project like that, the Roadmap Epigenomics project, and most recently a very interdisciplinary project that is aiming to, which may seem somewhat anathema, to kind of remove the sequencer from genomics and push the whole thing into microscopy.
Thank you. As you can tell, we've got a very well-qualified and interesting panel, so hopefully have an interesting discussion. I want to get into some of the details on, what makes a good scientific team. But before we do that, I wanted to just take a little bit of a step back and look at the question of what's driving this trend, and I'd love to hear from John as well as Michael from your perspective on, is it the science that is sort of forcing us to take another look at the way the academic institutions are structured, the grant making, and the way commercial ventures are structured, where there's a financial incentive, intellectual property, and all of that. Is science really forcing us to take a look at that and reassess whether there are better ways to accomplish new things and innovate? Or are we ready, whatever that might mean, to embrace sort of a new way of going about science?
Which one?
Anyone.
Do you want to go first?
Well,
actually, can I ask just a clarification? So what do you mean by science forcing us? What do you have in mind?
Well, do we have, for example, genome, big data? We've got a lot of trends going on now that seem to almost cry out for collaborative efforts that, we hear a lot of people say, well, this is something that is only possible with, the help of a multi-center, collaboration group and consortium, that type of thing. I'm just trying to get at, are we really being forced to do this, or is there something kind of growing and bubbling up now that will be, that will help us to better kind of create an environment for this type of collaborative work?
Right. So, obviously, you've sort of put your finger on at least one forcing factor, which is the ability for relatively small capital expenditure to generate enormous amounts of data, where the original team has no hope of getting all the value out of it. You're far better off to take your petabytes of data, or small data, terabytes, and open it up. And I don't know, things like the Sloan Digital Sky Survey in astronomy, or obviously the human genome data. I think in the case of the Sloan survey, there's been 4,000 or 5,000 papers written based on that data, and obviously there's no way the original team could have done that on their own.
Well, I might add, you've got kind of the data side of it, and also you need technologies that will support the investigation. As Thomas Kuhn said, you've got to have these discoveries that change the paradigm so that you move to a different way to look at it. And if you look at his study of breakthroughs, there's always an enabling technology that at the time gave something that was a piece of data that was unexpected. And from my viewpoint, it is the integration of technologies and the technology to enable the research that is so important and growing.
And does that make it more sustainable in a way? That it's not being sort of artificially forced on,
once again, if you have the goal of discovery, that needs to be there. Even though I'm an engineer, I view myself as supporting the biologists to get there, and that makes it more sustainable.
John?
So I think to your original question about what is forcing or is there something forcing the innovations at the science? I really think it is, and it's something I think that gets down to a very, very fundamental level, and that is the question which drives a lot of science, which is simply, how does this work? How does it work? And it is this inexorable drive to answer this sort of basic question that all scientists kind of have inside them that moves things forward. You look at the Human Genome Project. There was a tremendous amount of focus on just getting the DNA sequence. Once you get the DNA sequence, the DNA is inert. How does it work? How does the cell actually work? And this is what is continuously driving. So this question then drives the technology. And I would agree that technological developments are the lifeblood of innovation because and one goes through a cycle then of asking the question, how does it work? Developing technology to acquire more information, because this is the legacy. I mean, if you look at 2,000 years of sort of scientific innovation, intellectual innovation, these did not come from hypothesis-directed research, because that assumes you already know the answer. What it came from is repeated rounds of invention of technologies, the telescope, collection of data, putting the data together, coming up with a model, and then moving forward, but again, continuously pushing the technology. So I think that that's a major driver.
I'm sorry, I got to step in because it was a hot button. After the genome, and just as you said, well, how does it work? How does the cell really work? You see a lot of work on cell signaling. So this is the details of the dynamics of the cell. And if you look at the technologies in the biology labs, and this is what kind of caught my attention when I started working in Nobel Prize-winning labs, these are gel electrophoresis. These are 40-year-old technologies to explore the dynamics of something that they can only take snapshots of. And so I submit that to move to the next step is going to have new technologies.
I think from my perspective, the issue is that the scientific challenges that are exciting in the future are very complex, and they transcend any one discipline now. They really do require multiple disciplines to come together, because it's at the interface that things are becoming very exciting. It's no longer within a singular discipline. So I think that's part of what's forcing the team mentality.
Yeah, I think that's an interesting point, and I want to now go to, John, let's start with you there at the end, about how it's good in theory, it's multidisciplinary, and we hear a lot of talk about, groups coming together from different disciplines, even putting them in the same building so that they can actually, meet over coffee or run into each other in the elevator and have these discussions and generate sort of the ideas that are the lifeblood of this kind of innovation. But it seems that our structures, our infrastructures, and our incentive systems, you were just raising the question earlier about the tenure system, sort of discourage that. So I would love you to just address, perhaps we can go down the line to some of the biggest challenges to this, of making this team-based approach a success, and how you were able to overcome them.
So I would distinguish here two types of team science. One type is the type that has been referred to now several times, this sort of idea of pushing disciplines together to solve problems and create new knowledge. The second one is to take a number, which is more the paradigm of some of the team science efforts that have been involved in, like the ENCODE project, which was to take a number of technologies run by individuals at different centers, and each of those centers may have had interdisciplinary sort of groups blending biology and computation, for example, together. But then that whole project was working towards a particular goal. And the goal was defined by producing some type of increase in data or increase in knowledge. And so that's one type of team science that lends itself, that really intrinsically has no barriers, like tenure or the university structure, because it is a literally, in this case, was an international group of 5 or 6 centers that were working together. There, the success was determined by having a little bit, I don't want to say a benevolent dictator, but sort of a benevolent and informed people holding the purse strings
Right.
that enabled the project to move forward with a continual focus on the big picture project and not let people go astray too much. And also having communications infrastructures. And this is the kind of thing where the teams just learned how to work, how to take advantage of the web and other things to communicate results. And I think that, so I've actually been in 2 projects that have been like that. One started about 2 years after the first one, and interestingly was able to borrow many of the lessons learned and then got ramped up quite quickly. And then the second kind is the purely interdisciplinary kind. And now being involved in a project that has everything from microscopists to nanotechnologists to physicists, et cetera, all put together. But there also it's unified around a question. The question came first, and then was how can we put the pieces together to solve the problem? Now, barriers to that, I mean, and maybe I'm a bit of an anomaly because I've always just tried to pretend there are not barriers and try to move ahead and put things together and worry about the collateral damage afterwards.
But there are clearly going to be issues of who does what and people feeling that they are better equipped to do X versus the other person, and why is that person doing this? And I mean, the classic issues when any kind of group tries to do something.
So you have hit on something which is true of both of those kinds of team science, and that is that if you set up a situation where people within the group are competing with each other for some ulterior motive, then there's going to be problems, and those problems can metastasize. And so I think it's very important to have groups in which everybody has recognition of the other's expertise, understanding and respect for it, and understanding of the role that they're going to play. So the better those roles can be defined, the better it's going to work.
At the outset. And issues such as, when the paper gets published, who will be where on the list of authors and that kind of thing. I mean, these are issues that have become barriers to making these types of things happen, right? For, everything from funding to credit. So working those out ahead of time, you're saying, is one of the keys.
The more clearly those can be specified in the beginning, the happier everybody's going to be, that's for sure.
Okay. Other comments?
Can I just make a comment to connect, I think, your question to Michael Crow's talk before. He made this very strong statement about not being isomorphic to everybody else. And I guess the flip side of that statement, which he didn't dwell so much on, was, of course, that there's an enormous amount of pressure to do the same thing as everybody else. And the reason is because there's a relatively small number of narratives which are current at any given time. Here's the hot topics, here's the hot fields. Everybody knows this. And so it kind of acts as this bottleneck which everybody tries to channel through, this is a big institutional constraint in terms of how teams work, what they are able to work on, and in particular what they're able to get resources to work on. And it takes a very clear statement, preferably coming from the top, that we're not going to do this, and that some of the time we're going to, we will lose out because we're not doing that, and you need to be willing to pay that cost.
Have you seen examples of, sort of innovative ways that those types of barriers are intentionally brought down so that that kind of competitive atmosphere that seems to be ingrained, in our system is sort of minimized?
Well, creative ways. Certainly Michael's approach of standing up. It was really interesting. I flashed back to an interview. As he was speaking, I flashed back to an interview I heard with Steve Jobs being asked, how did you turn Apple around in 1997 when you came back? He said almost exactly the same thing. He said Apple had become a company that thought that we needed to be as good as Microsoft and we needed to compete in those markets. I decided we don't want to beat them on the operating system. We're going to do something completely different. We have to invent new markets. And so it's the analogous statement. So that kind of clear statement from top leadership, preferably, in my opinion, accompanied by a willingness to take some hits, is a big thing.
I could chime in. Working in teams on both coasts, what I've observed is the biologists tend, when seated in the room with the technologists, the physicists, the engineers, and we're talking about where we want to go, the biologists tend to think in what I call RO1 bites. This is because they've been schooled over the years that they're not going to get funded if it's bigger than an RO1. And it's hard to break out of that conversation because of that mentality. And it traces back to the very beginnings of NIH. I mean, NIH was started, as, in sort of the concept of the single practitioner. And, most of the funding from NIH, 94%, is RO1 scale. That's a single PI. If you've got team science, and the way I look, and my team science work is with engineers, they are inherently going to more than double the cost because they're going to be inventing technology which takes time and money. You're automatically out of kind of the, not just the funding, that's part of the story, but you still got the mentality that kind of has been beaten into people over the last few decades. And breaking that, saying, no, we've got a different approach, we've got different funding, and we do in a few instances. It's still very hard for a biologist to offer a hypothesis that is of a scale bigger than what they know they can get funded.
I think what you've hit on a very major point, which is the fact that technology development and innovation per se is not funded. I would bet that if somebody really went and did a study of the NIH and said how much of these actual real innovations that came through were actually funded in people's grants, I would say that number is probably less than 5%.
Well, the interesting one is who was the initial funder of the Genome Project?
DOD.
DOE.
Or DOE, sorry, yeah.
And, and I think it's difficult for NIH to comprehend in their structure how to really manage technology. It's a tough thing.
I mean, I think that this is where what I meant by this sort of the benevolent funding agency comes through. Because I think that, the lesson of a project like the ENCODE project, this project started out and it had, it sort of went through this pilot phase of a few years, back in 2003 to about 2007, in which you had a series of technologies that were funded. The purpose of the project was, we're going to apply all these technologies to kind of 1% of the genome, which at that time was outrageously ambitious because most people were used to working on little tiny chunks of, minuscule chunks of genome using these older technologies. And then they were going to evaluate things, and then it was going to go on to another phase. Well, what happened is nowhere in this structure was any innovation built in. You had a technology, it was approved, you're going to apply it, and we're going to find the results. But what in fact happened is that every group figured out ways of creating operational efficiencies, taking advantage of technological developments and dropping costs of reagent to create basically what we nickname, we literally call this science venture capital, okay? So it's essentially, you're now creating this buffer that allows you to meet your milestones and still have money left over to play. And so what happened is then everybody showed up when the project was going to be scaled up to the full genome with all these new technologies. And fortunately, the program staff never asked where these came from. Where did the money actually come to do all this? Because they just kind of turned a blind eye and knew that what people were doing. So they tolerated this innovation that was going on. Right, but funding innovation itself is not a process. Yeah. Well, believe me, I sit on study sections that see many innovative things, and they just just technology development gets killed every time.
Right, but it would take, as you said, it would take someone at the top to recognize that you have to set aside, instead of continuing on with the existing technology, set aside some chunk for innovating and making sure that you're keeping up to date with where you're going. You want to be in 10 years, not where you were 10 years ago.
Right. And what's happened is people just found a workaround because
Yeah.
it was mentioned about these R01 projects, these investigator-initiated projects, which are typically evaluated, typically sort of boxed up and evaluated on in a very sort of rigid way based on hypothesis and other things, versus these team science projects. Well, these team science projects, we're on the phone and interacting with other members of the team and the program staff multiple times now per week. Okay, so there's huge surveying of what's going on, and yet you can still do the innovation. Whereas those other investigator-initiated projects, they check in once a year. So in fact, what people have done is, the way people have funded innovation is, get the money to do X, but forget it, we're not going to do X. We're going to go after this. We're going to go after something really innovative. And if you're not trying to renew that project, fine. If you're really an innovator, you'll just get another one and another one.
But you're
And
also saying that there needs to be flexibility, in other words, in which there really isn't, right,
Yeah.
in the current system.
Yeah, so people have some things that people have
Yeah.
sort of gamed the system in order
Yeah.
to fund real innovation.
Right. Go ahead.
It's been my experience that teams have a real hard time seeing their own problems. No matter how innovative they are or whatever, teams and team leaders especially don't recognize their own problems. And the best way in the teams that I've created and funded, the best team leaders have been team leaders who are not skilled and experienced in the discipline they're leading. They're highly intelligent individuals who become self-educated in those disciplines, and they have the ability to ask the questions that the team members themselves can't ask because they can't see past their own experiences. And so I think that the people underestimate the value of the shadow that the leader casts over the entire team.
But what you're hitting on also is the primacy of the question. And this really is what, so earlier you asked this question about big data. And about, the problem with the whole big data idea is it's also this problem of kind of bioinformatics or biomedical computation, this whole idea that we have all this data out there, and that if we just threw all our algorithms and whatever, that some knowledge is going to come out. Well, this is not a scientific, this is a religious belief. This is not a scientific belief, right? And because there's no real evidence that connects the dots. And what I have found is that the problem with that is that everybody jumps in with their favorite algorithms and then starts, this sort of, and this is kind of a big divide, I would say, in many of the sciences that we've interacted with, is that there are people who have the engineering mentality, which is, I want to know how it works. And then there are people who have the algorithmic mentality, which is, I invented this algorithm, let's go try it out. And then if it doesn't work, we'll refine it and move to the next. They're not really guided by the question. But one good question trumps all of that. It's just knowing how to answer the right question. Suddenly you don't need, 50,000 cores or whatever to answer your problem. You can do it very cleverly if you just ask the right question.
You raised an interesting point I want to get into. There was some interest in understanding how to make the best of failures, because every project, every experience is going to have its ups and downs. But how do you know, and I think you're making the argument that it would take someone who's not so invested or, has as much experience in the actual discipline to sort of be able to step outside and see when things are going in the wrong direction. What other strategies have you looked at or tried, either successfully or not so successfully, to recognize failure and to learn from it?
I have some very specific examples on this because the fundamental problem with failure is everybody wants to deny it exists at all, okay? So you can go in a project in which people are producing data and what is being measured is just the amount of data, not whether it's any good. And so once you start introducing metrics for determining the quality of what's being produced or some independent standard, then suddenly you have something you can understand. This passed, this failed. So the first step in failure is just to acknowledge it exists, develop some objective way to measure it, and then once you can, then you can build around it. And for us internally, this actually revolutionized the way that we approach things. Because once you had metrics for really understanding whether this experiment produced good data or not, then suddenly, then grassroots innovation takes over. Then somebody comes up and says, you know what, I came up with this great idea, and I kind of tested it. I know we didn't tell you, but it did this, and look at the results. We can prove that this now works better than this. So I think that's an important, way of, and it's also definitely encouraged. So once you can recognize failure, you have to encourage ways, around that to improve the process.
I'm wondering, are there examples from engineering that we can learn from?
Well, certain, that feels like that got tossed in my lap. So You know, I think I'd like to put it in context. In doing the research, I found two particularly outstanding organizations to the point of success in teams. It was back in the 50s, and one of them was actually not far from here, which was the Rockefeller Institute, and the number of Nobel Prizes in biology that were done with teams that were both biologists and engineers, where the engineers developed the enabling technologies. Once again, it was gel electrophoresis back then and some other archaic technologies now. And the other was the Laboratory for Molecular Biology in the UK in the 50s. It was quite astounding. They accounted for 12 Nobel Prizes in biology with a faculty that was not much bigger. And if you look at it, what was underlying it was they made Max Perutz, who was running it, made a commitment to X-ray diffraction and driving that as hard as he possibly could for new technologies. So going down both the biology side as well as the technology development, bringing X-ray diffraction to a point where they could differentiate molecules that they needed to, as well as electron microscopy. And you know, of course, some of the X-ray diffraction work led to the double helix, et cetera. So and Max was, I think, the driver. There's a book about him that shows this relentless drive past many failures. And the other side of that is their funding. Once again, both Rockefeller and Laboratory for Molecular Biology had this basically tenured kind of funding. They could continue without worry about what the next year was going to be. And I think that is unique, and it was wonderful. You know, you asked the question about the other side. You know, if you look, the world I came from was a lot of work in high energy physics at Lawrence Radiation Lab, and then in semiconductors. And there, all the research was team. There was no other concept. How could you build an accelerator? You know, it's a physicists and chemists and engineers, you know, and if you look back in time, it's always been that way in the, once again, the Nobel Prizes in physics are always physicists building the technology that's needed to make the breakthrough. And so I think it's a different orientation, a different culture. But I think there's a convergence now that I think is bringing that into biology.
One of the big problems with trying to learn from failure is that failures are not published. So everybody has to relearn the same failure. And the issue with R01s not driving technology really has to do with the way the questions are asked. If you change the question, and really somebody earlier in one of the discussions said that most of the issues and failures occur at the back end, not the front end. And if you go all the way to the beginning of the back end, that is what the question is being asked. The hardest part in trying to drive technology change and to drive innovation is to frame the question in a way in which the path is not obvious. Because if you take the obvious off, then all of a sudden the scientist is forced to recreate and rethink because the traditional thinking doesn't get you to the linear answer. And when you do it that way, even a small, modest amount of money can get you significant amounts of innovation. So if you spend 98% of your time reframing the question in a way which you know that you can't get to the answer, then the failures become obvious much quicker, and the innovations become much more significant early on.
I'd like to just hear, is this how it's done? I mean, if we were looking at kind of just the balance of the time and effort spent, you know, how much of it is really in that front end, planning, organizing, and you would make the argument then that probably not enough is at this point in order to make the most out of that team experience?
I think that's true. It's not done enough, but where it is done, there are tremendous examples of success, and the success rate is much greater.
Michael, it looks like you have a comment.
Can I just interject? I think failure is getting an unfairly bad rap here. if people talk about doing high risk, then by definition, they are failing a substantial fraction of the time. If you are not failing a substantial fraction of the time, you are not engaged in a risky project. An idea I've tried to push at a couple of foundations is that at least a few of their programs, they should have failure audits. And if they fall below a certain level, then questions should be asked. They are not engaged in risky activities.
Can I address that more specifically? That is exactly what we do at DARPA, or I don't speak for DARPA anymore, I should make that clear. But at DARPA, the whole idea and the whole ability to take these huge risks is because there is no consequence to failure. When you take the consequence of failure off the table, then amazing things happen. I don't know how many people here are familiar with DARPA, but it is the Defense Advanced Agency's, the Defense Department's Advanced Research Projects Agency. And it's brought some pretty amazing things over time. And frankly, if DARPA were a brand, and you say DARPA inside, you'd be really, really surprised about where you would find DARPA in terms of everything from ballistics missile technology through to your telephone today, your cell phone today, Siri,
right?
prosthetics in the medical area. In the medical area, also the whole brain-machine interface now was a function of DARPA. Freeze-dried platelets just came out, function of DARPA. There's a whole lot of things that one could say in basic physics, the physics of slow light, and at the other extreme, the attosecond pulses for lasers and how that changed the whole world of physics as well. But all these are incredibly high-risk opportunities. But when you have a steady budget of $3 billion a year and only 120 people to spend it, you get amazing things happen.
There was I have to support this and say there was a wonderful article written by an NIH person about, does NIH need a DARPA? And you need to be careful, and they don't need to just set aside the money like DARPA. They need to have the culture of DARPA. The difference is DARPA program managers put themselves at risk. They go out there, they figure out what the unmet need or the challenge is, they articulate it, they fight for it, they get the money, and then they fund it. And once again, the NIH world supporting biology and medical research is very different. And it's going to be hard.
They've already proven it's a failure. If you look at the intelligence community, the energy community, NIH, they've all tried to replicate the DARPA model and have not succeeded.
Yeah, internally.
And have not succeeded.
Right.
And part of that is because everybody still has the culture of accountability except within DARPA.
Right.
There's such a mass of money there that there's always a good story to tell for the agency. And the individuals are never penalized. And to your point, Michael, you're right. If our best program managers failed often, and some of them failed very spectacularly. And it was the program managers who never failed were the ones you tried to get rid of through whatever means you could.
So other than instituting a sort of failure tally system to rival the tenure system, how can that culture change? What is it about, other than, the kind of environment that DARPA, what is it in the water for DARPA that's different?
Well, it's a leadership issue.
Mm-hmm.
But DARPA per se is an organization under continuous pressure to change. So the DARPA I'm talking to you about is not the DARPA that exists today, and it'll change again tomorrow. It's a continual metamorphosis. But the leadership, as Michael and others indicated, has to be willing to say that we're responsible, not the individuals. The other thing that we do that's very, at least that I forced to happen, since gone by the wayside, but DARPA is a place for ideas, not careers. The minute you start mixing careers with ideas, bad things happen. So what we did was we forced a rotation policy. 25% of the staff has to rotate every year. What you get then is an environment where old ideas become new ideas a couple of years later. There's no institutional memory to say that can't happen. Been there, done that. When you eliminate that, then you get where technology has now advanced a little bit, new ideas become possible. There's nobody to say it can't happen, and you can try it again.
This sounds super top-down. I mean, honestly, I think if our program people had the same kind of power in whatever DARPA did, all of our projects would have failed. I mean, really, because not because they're not excellent program managers and also former scientists, et cetera. It's just that my experience has been that the more top-down that things are into, that the real innovation happens at the level below program, and that what program does is act as an enabler. They enable it, and with DARPA, probably it's just, it was the confidence of the program officer to say, you know what, I'm going to invest in this big area. I'm going to find some guys to do stuff, and but the innovation's going to happen at that level. It's not going to be run up at the top. So I think the more it's run up at the top, the higher the risk. And I think that this has to do also with a question that was asked earlier by Alice, but I think it extends up to this: is how is failure and what's the process, and how does this actually impact the team? And this is from the low-level teams to the high-level teams. And that is that the team leader, because failure is intrinsically extremely disappointing to people, and time and again, you see somebody does the experiment, oh, it failed, I can't, it's not going to work, it's just not going to work. So what the team leader is doing is they find themselves in the role of the relentless cheerleader, right? Try something else, try this, try that, and that works at the level of the team, and I imagine that works at the level at the program, which is, all right, fine, you guys failed, let's try something else, do something else, and that's that you need, that relentless cheerleading to get through the necessary failures.
And part of that cheerleading is encouraging people to go outside of their comfort zone, to talk to other people, to get new ideas to come in. But it is true that at the end of the day, people have to win and people have to lose. But the program goes on because what you end up doing is competing multiple competitors to do the same problem. So, and then again, in the RL1 sense, it's the definition of the problem that's everything, because if you think about it and you're creating multiple new creative solutions to the same problem, then some will fail and some will succeed. And it's very painful to fail, but that's at the performer level. At the programmatic level, they've got their winner because one of the four advanced and went through. It's true.
And how important is the post-mortem for those failures? I mean, I've talked to people who I think spend an inordinate amount of time in postmortems and sort of going over and over and not really learning. How do you make sure that you learn from that analysis and go forward from, to the next problem, why this one failed, and applying that lesson to say, what do we need to change in order to make this work? Or as you said, keep trying, but don't try obviously the same thing, but do it in a different way.
So I remember seeing, I think it was Michael Nielsen from Saturday Night Live saying that after each show, they spend an hour that night doing a post-mortem. So it's quick, it's immediate, and there's still, there's more stuff done later. I think he watches the show on Monday again just to see how it was. But they do get that instantaneous impression, and it's quick. It's relatively painless. I think it's nice to have it built into the process in that way.
Mm-hmm. This is actually, the post-mortem was an intrinsic part of the fabric of learning medicine, right? You had a patient on the ward, the patient died, you went to the patient's post, and you really understood, okay, this is where I screwed up in the diagnosis, or that's what that looks like, et cetera. And the problem is, as time has gone on, is that the post, which used to be done almost routinely on every patient, 30 years ago or 40 years ago, now just trickled off into being this anomaly that gets done. So you lose that immediate feedback, which I think is really important. I think, but also in science, the problem right now is that like in business, when business fails, they get a postmortem, but it's done by business schools, right? But in science, there's no business school equivalent out there doing the posts on it and publishing the studies to say what happened. And the problem is that everybody's just so continuously busy that I find that we just do not take that time out to go back and say exactly what happened here. And the problem is, it is a painful process. So, I mean, there is this process, let's say in medicine, it's the weekly morbidity and mortality conference. You had a patient die unexpectedly on the wards, you're going to be called to task. What happened here? And it's an embarrassing and sometimes uncomfortable situation to be put on the spot in front of all of your colleagues. And people just want to avoid that. So the only way you cannot avoid that is to institutionalize it. In some way, it just has to be there.
Go ahead.
My experience is that there are two levels of postmortem. One is the individual performer, what they can take with very quickly on a snap, and the other one is what the institution deals with. And I'd say over 70% of the institutional failures at the postmortem level are all a failure to communicate. It's a failure to communicate within a team, between the teams, and that's where the institutional learning really could help team science, is in institutionalizing better communication methods and better metrics for the individual team members.
And I would say there's one situation in which there can be great communication between the teams, but things still can fail. And that is when the sociology, see, what happened is there was an original idea, a goal, the team was assembled, the team went to start moving towards that goal. But then the team built a culture. And then suddenly that culture started to be more important than the goal. Maintaining the culture. So when the program is, let's say when you evaluate a project or something, it's not, dropping out parts of the team that are not, that are not actually producing towards the goal, but are, become sort of culturally ingrained in the process. I think that's a very dangerous thing that starts to put people in the path of
because then it maintains
failure.
the status quo, right? It doesn't innovate. It doesn't.
And not towards the goal. It's part of the social network essentially, rather than the science network.
Interesting. Okay. Well, we have a few minutes left. I want to make sure we give our audience a chance to jump in and ask questions. If there are any, I don't know if we have some from.
Alice.
Yes.
There's I think a great question in the Twitter stream.
Yes, I'm looking
there.
at it right now.
How do you account for the fact that some failures were ill-advised in the first place instead of simply ambitious? And that's a question we really didn't address, and it's a pretty hard one, I think.
Yeah.
It didn't seem ill-advised to the person doing it, or they wouldn't have done it.
Right. It's a fine line, right, between that, let's try and try to innovate, and something that's misdirected, because you can make the argument before you do it. How would you know?
Yeah, I mean, I think a lot of people, you can pull many examples. I think the interesting examples often are things which really probably did seem stupid to most people at first. Twitter just IPO'd, I guess, and here I am reading a question off Twitter, and yet I think most people's response early on was, this is a ludicrous idea.
Right.
So it did in fact seem ill-conceived.
Yeah.
Well, I can't speak so much for the field of medicine now, but when you get out of medicine and you start looking at technology development and ideas, people look to the customer for the ideas and the development. And sometimes that's the worst thing you can do. If you are trying, the closer the customer is to the question, the less innovative the solution is going to be. The best recent example I can think of right now is unmanned aircraft. When a program manager set out to develop unmanned aircraft, it had to become a religious passion with the individual because the customer didn't want it. In fact, the customer, the Air Force, actively, in the pilot culture, actively tried to kill the program for a couple of years. So it was important that the people let the program manager go with obscene amounts of cash, obscene amounts of autonomy, and competitive programs. And in the end, you have a solution now which would not have occurred if the customer had been involved.
This is the Henry Ford, problem. Like if I'd asked the customer what they wanted, they would have said a faster horse, And so I think that's exactly right. And at the level of universities, the place where this really matters is in the intellectual property office, because you go, and so we recently had a change in our regime in our institution. And the old regime, you would go with them to with an innovation, and we'd say, look, we know this is going to be important, and they'd be like, well, we can sort of, what we want to do is kind of float the idea to some people who might potentially license it, and then if we get a positive response, then we'll patent it. And what our ultimate result was, fine, we're just not going to go to you anymore. So we'll just continue on spending millions of dollars a year on, on all these projects, producing lots of innovation and publishing them, and you're just going to get nothing. And what's happened is the new people have come in and said, oh, we want to take a look, and we know we want to invest in the potential, and we'll see, because ultimately they can't predict the successes and what really, counts as the blue. So that's a really important thing, is get away from the customer. I think it's very, very important insight.
Well, let me add a sort of a historical perspective. When I went back and looked at now 40 Nobel Prizes and tried to understand kind of the underlying enabling technology behind them, because there's always one thing. Of those, 37 of them didn't have a concurrent technology development. And if you look at all those, the technology that enabled it was generally developed on the bench 40 years before that. It took about 30 years to make it to the market, because it made it to markets that had nothing to do with kind of the biology need. It was just driven by commercialization. And then once these things became available to biologists, it was 7 years on average to publishing the Nobel Prize winning work. I think that the customer doesn't speak for the biologist. And I think and this was kind of my theme about the downside of not having team science. When you have to wait for the technology to make its way through the natural processes, those are going to be driven by factors that are outside of what the biologist or the researcher needs, and there could be a 30-year delay.
We do have a question about greatest failures and what you learned from them.
Nobody wants to admit that, right?
It's hard.
God, there are so many. Because how many failures do you count? How many bodies are counted on the way to the success?
Right.
There are so many.
Perhaps one of the ones that turned out to be one of these, it turned out to be misdirected, but it was hard to tell from the start.
Well, I was actually coming out of my fellowship training. I was involved in a biotechnology company. And the company was based around essentially the exact same science that we have moved forward over the years with. So the science was, and the goal, everything was extremely sound and turned out to be extremely productive. But the failure, which taught me a lot of lessons, came at the level of management and implementation. And particularly doing sort of a postmortem, on this, is thinking about what were the sort of the key determining steps, and there were, and you talk to people in biotech, and they will tell you, you hear this refrain many different times, which is that if you get, for example, the wrong CEO for a company, then suddenly, and there's a culture, then it can really pervade, the whole thing in terms of steering things sometimes into the ground. And so I think that, learning how to match. So that taught me that you really have to have a very close match between the people who are organizing and doing the science and people who are sort of kind of managing the enterprise, and I think that was there were fairly painful lessons there, but definitely important ones.
I think that's two universal truths in the transitioning, in the technology transitioning area. The people kill it, and undercapitalization kills it. Not enough money and the wrong people. Either of those are very toxic mixes.
Okay, I want to have a question from the audience here.
Hi, thank you. So you guys talked a lot about ways to fund team science. It seems like a major topic. And on one hand, there's sort of a resounding support for a lot of leeway and creative ability in terms of fostering innovation. On the other side, the need for accountable metrics in order to assess progress, and also the need to do post-mortem analyses and analyze failures. So these sort of seem to be, in conflict with one another. Can you sort of address how to best achieve that balance, and perhaps more examples like DARPA that you think do it well?
I don't think that metrics and accountability and flexibility are mutually exclusive at all. I think what a metric is good for is to tell you whether you're on target or not on target, and if you communicate well with your other team members, because at some point in time, your program is rate limiting to their ability to progress the team effort. So what's really important is that you set timelines for yourself that other people understand, and then you work backwards and say, can I meet that timeline, can I not, which is always done in the planning. And then the issue is early on when one thinks it's not on track. Then the metric is really useful to say, well, now I better let people know, A, maybe they have other solutions to help me get on track, B, and or C, to go out and ask for other people for help. But the metric isn't meant to be a punitive thing at all. What it's meant to be is to help you assess whether you have to take a different approach in order to find a solution to a hard problem. And I think if metrics are used that way, then it's really not threatening. It's an enabling tool for you and the other team members.
Yeah, I guess I think the DARPA model offers some insight because the metric needs to be, as you've said, at the program level so that you know how you're proceeding. But it's the program manager who's really like the venture capitalist, if you will, looking at 4 or 5 programs. And that person is hoping that one of those 5 is going to succeed, not all 5. And that's where the risk can be taken. And so I think it's a matter of where in the funding hierarchy that the risk is taken. Once again, at NIH, it's all on an individual basis. There's really no program manager risk. Everything is peer reviewed and it either gets funded or not. And I think that is an element of what I believe needs changing.
I think that's a good place to stop now. I want to thank Alice and the panelists. A very stimulating and challenging discussion. Thank you.